Hi again. No trips out to play video games this weekend, I'm afraid. I've just been helping the boys with a bit of maths homework and looking at the marvellous complexity buried within fractals. These spiralling patterns that are continuously revealed as you delve ever deeper are amazing. It seems almost ludicrous that such complexity can arise from such simple formula, with the application of just the same basic calculation over and over and over again, and applying a colour palette to represent different numbers. You get these organic, almost alien shapes and patterns. And it's no accident that we see fractal patterns so often within nature, with everything from ferns and cauliflowers to lightning forks and coral reefs being made up of self-similar patterns. Complexity built up from the application of simple rules seems to be nature's way, and therefore we see these organic qualities appearing within the branches, tendrils, swirls and voids of the Mandelbrot fractal set. Minds too seem to be the result of complexity from simple patterns. While AI systems gain much press because of the new capabilities they present compared to computing systems of the past, the reality is that the overwhelming majority of AI systems use the same logical processes that have underpinned computing since the 1940s. While there are notable examples of neuromorphic AI hardware that seeks to closely mimic the spiking activation of neurons in the brain, with examples from Manchester University's Spinnaker project, BrainChip AI's Akida processor, and Intel's Loihi, these are the exception rather than the rule. Most AI runs on the same type of computing hardware as more traditional systems, with arithmetic logic units built up from logic gates, built from transistors, all running to the drumbeat of a single system clock. In fact, an AI is really just carrying out the same relatively simple calculations over and over and over again. You can think of each neuron in a neural network as taking inputs from the neurons in the immediately preceding layer, multiplying those by the weight of the relevant connection, summing the result, and then normalizing that against a curve to get a value within the correct range. Each of those actions is so simple that you can ask a primary school child to perform the sums. The only difference is that an AI system might be made up of millions of neurons with hundreds of billions of weighted connections between them, and even the cruelest maths teacher wouldn't set that as homework. In reality, systems don't need to calculate the values for each virtual neuron within a neural network individually. The relationships between layers can be represented by massive matrix multiplication operations instead, exactly the types of calculation that graphics processing hardware is good at. So you can go from a bit of Cyberpunk 2077 to generating steampunk art using stable diffusion on the same graphics card. The amazing capabilities that AI systems show are an emergent complex property of simple rules being applied millions or billions of times over. And this makes it very difficult to clearly define AI systems. And that matters if you're trying to write laws or policies to control the use of AI. Let's take a look at a couple of examples of how legislators and regulators have tried to address this problem. In the EU's forthcoming AI Act, the relevant definition is AI system, which reads: Artificial Intelligence System, AI system, means a system that is designed to operate with elements of autonomy and that, based on machine and/or human-provided data and inputs, infers how to achieve a given set of objectives using machine learning and/or logic and knowledge-based approaches, and produces system-generated outputs such as content, generative AI systems, predictions, recommendations or decisions influencing the environments with which the AI system interacts. This definition casts the net wide. The references to logic and knowledge-based approaches will mean that many systems that are not machine learning systems, without a neural network in sight, will fall within the definition. To prevent the regulatory burden being imposed on too wide a class of AI systems, the AI Act then goes on to regulate systems according to the use to which they're put. Some uses, such as systems used to cause harm by subliminal means, are prohibited entirely. Other use cases, such as using AI as part of a safety system for a CE-marked product, or using AI to make decisions in the context of employment, or determine access to essential services, are considered high risk and require operators to comply with a variety of record keeping and validation obligations. The fact that high risk use cases include deployment of these very broadly defined AI systems for HR purposes means that it's likely that many businesses will find themselves having to comply with the AI Act. A different approach was seen in the UK's policy paper in July 2022. Rather than a single sector-agnostic horizontal regulation, the UK proposes a sector-by-sector vertical approach to the regulation of AI. In order to provide some cross-sectoral consistency, the policy paper sets out a series of common principles to be applied, such as ensuring that AI is safe, trustworthy, transparent and explainable. The policy paper does set out a definition of the types of AI to be regulated, with greater regulation to be applied as systems become both more autonomous and are more potentially unpredictable because of adaptive styles of training. This seems to be a useful way of categorising the types of AI most likely to lead to significant issues in practice. Any system that is entirely autonomous but fairly predictable, like an ATM cash machine, presents little risk. Similarly, a system that is the result of adaptive training but operates in an entirely supervised fashion might generate errors, but that presents little risk if any errors will be caught by the supervisor. It's where systems are both autonomous and the result of adaptive training that the greatest risks are concentrated. And it's easy to see how self-driving cars or unsupervised internet chatbots might fall into that category. Now, regulation is one thing, but many organisations are grappling with the definitional question for themselves as they draft internal and external policies regarding their use of AI. Where the policy is to assist with legal compliance, then it needs to encompass all of the emerging legal and regulatory definitions. And as a result, any AI definition in the policy is likely to be very broad. For most purposes, I suspect that a definition that simply reads any more than moderately complex computer system will capture anything that would fall within the EU AI Act's definition, without casting the net any wider for most purposes. Organisations can then ensure that their own list of high-risk use cases includes all those listed in the Act, whilst layering on risks to their own business, such as systems controlling production, supply, purchasing, trading, and other commercial risks which are not addressed in the AI Act. Now, there is a certain irony to all of this. One of the tasks that AI has opened up for automation are those that could not previously be computerised because of the problem of categorising or classifying things. Judgments that humans find easy were very difficult to encapsulate using traditional coding methods, and that's whether we're talking about classic image recognition or spotting patterns of behaviour that might suggest fraudulent activity or otherwise. Now, our neural network-based systems can perform at superhuman levels in many of these you-know-it-when-you-see-it classification tasks. There's a wonderful short-form podcast that I enjoy, where John Siracusa and Jason Snell try to answer the question, robot or not, for a whole series of machines from the real world and science fiction, whilst also occasionally straying into related topics like whether a hot dog is a sandwich or not. It's well worth listening to if you enjoy some humorous pedantry for its own sake. But if deciding whether something meets the definition of being an AI is so hard, and we now have machines that outperform humans at classification tasks, perhaps we should build and train an AI or not AI that can make the decision for us. In that way, the decision about whether something is an AI is left to AI, a sort of self-similar AI decision fractal, but in this case one that creates simplicity out of complexity rather than the other way around.